case right here, this would be two real roots. Real roots. That would be the first case. Actually, hang on. I'm gonna write this. That's the case. This is our answer. We put a box around it. This looks pretty. You have it in our toolbox. You can draw a toolbox if you want it. Maybe a fancy handles. Maybe some double heels on the edges. Make it look nice. That is what's in our toolbox, our fundamental solution. So let's look at our two real roots. One. Jeez. Couldn't figure out what letter I wanted to write. Two real roots. Two real roots. That's our solution. I'm just going to put the answer as G. What do you want? What else? What other cases did we have? Which one do you want to look at? Repeated roots, all right? Repeated roots. Oh, really? Now? I was hoping we'd run out of time before I had to deal with this. All right, but we might as well just slate it right. Repeated roots. Repeated. Actually, this one's pretty cool, I think, in a way. I think this is the most amazing. Repeated roots are this. Notice repeated roots, this means this is the case of, we'll say, for this case, how about we say that S2 becomes S1. Marceline, what happens if S2 becomes S1? Right. Ryan, since you wanted this one, what happens if you have 0 and 0? What do you do?
Or
Got it.
zero. Is it multiple?
Yes, very good. Yeah, exactly. So, nice. This is the case here, which gives, and let's make that note, comma, which is the predicament. Which is the predicament. People, if you're not a math predicament, did I spell that correctly? Is the problem. Is the problem of 0 over 0. I don't think people realize that this is like when the bad guy in a superhero movie has a bomb, right? But people just go, oh, it's 0 over 0. What's the problem? Math people are like, you don't see this? Oh my gosh. Yeah, so like Ryan suggested, we have to use L'Hopital's rule. That's our way to bring a lot of things to use. L'Hopital. It's a name. We're going to treat it as a verb because we're going to L'Hopital it. It's a noun, it's a verb. So what we're going to do is we're going to take the derivative of the numerator and the denominator. Now here's the part that I always have to just stop and think about. What becomes a variable? In other words, what's changing? Yeah, this is your key right here. Notice that this is the change. I'm going to just use a delta symbol. That's the change. In other words, S2 is your variable of interest. So let's make a note that S2 becomes the variable. S2 becomes the variable. So we're going to take the derivative of the numerator and the derivative of the denominator with respect to S2. So I always have to think about it because I'm always thinking that's a t or an x, and we practice that over and over in calculus. But that's the variable. T becomes the constant. So when you take the derivative of es2t, the chain rule is going to give me spit out a t es2. So let's I'm gonna leave some space. I'm gonna put my limit here in a moment. So this is just t es2t. How about the derivative of es1t? Those are all constants. Let's see that one. I like it. Except for when it's my favorite. You guys didn't think that was funny. I know, and you're like, that one hurt. Don't worry, it doesn't get better as you get older. Sorry. You make lots of money. You be successful. Start a YouTube channel. So A is a constant. So if I take the derivative of the parentheses term, the derivative of S2, that's just a 1. The derivative of S1, that's a 0. And we don't even have to worry about our limit as S2 tends to S1. Well, let's take it. Our limit then, this becomes T E S1 T over A. That's your second solution. We kind of expected that, but remember the rules need to hold. So, go ahead.
Is that S1 or S2?
It's becoming S1. S2 becomes S1. Yeah. S2 becomes S1. Correct. Yeah. It was here because what we said is if S2 becomes S1, then these are like terms, are opposites. And if S2 becomes S1, then these become 0. So what we had to do is write, okay, well that's a problem. So we take our derivative, and then after that, then you go back and you recheck by substituting the S1. So, I could have, maybe that wasn't proper notation. So I should write that the limit as S2 tends to S1. Hopefully you aren't taking notes in pen, or you just left space to make that change. All right. And so our solution G of T becomes T E S1 T minus E S1 T over A times sorry, hang on a second. There. Solution becomes that. looking at this unique null solution. We're looking at this unique null solution. Yeah, it's like a very particular solution. Okay.
So, if we look at it the other way around, like as S1 becomes S2, would we reach the same conclusion?
Yeah, you have a change of a minus sign.
Okay.
Yeah, change of a minus. All right, let's try that. I'm waffling right now, and I have to admit, because I believe the A stays here in both of these, because it can't, the S1, S2 minus S1 can't stay, because then the whole problem becomes undefined. And but you need two roots. So I'm pretty comfortable with that solution. I might have to revise it. Okay? But I think that's it. I know, that wasn't a very good answer, was it? Really checking. I didn't think the author writes the whole solution. Sorry. Okay, I hate to do this to you. That's the solution. I know. I'm gonna leave this one for a moment. I might have to come back and rethink that. I apologize. I'm positive on that one. I think that's the correct solution, but I'll get back to you. I'll just post it here. All right, but we're not done. We've got two more cases. Do you remember what they were? Yes, okay, so the idea now is if we have complex solutions. So complex solutions provides two more possibilities. Okay. Number 3 is S is equal to A plus or minus I omega. So let's put that in. So I have G of T is equal to E raised to the A plus I omega T minus E raised to the I minus I omega T over A times S1, that's A, or no, S2, I have S2. So A times S2 is this one, A plus I omega minus parentheses A minus I omega. Parentheses. We have to put all of that in. Those are our S's. Let's clean this up. So I'm going to do a few things as we go through this. Notice that I have a common factor here of e to the a and an e to the a in the second term as well. So let's factor that. E raised to the a, parenthesis, this is going to be e to the I omega t minus e to the minus I omega t, parentheses, over what? A, capital A. Oh, look at this. We have an A minus an A. That cancels. I have an I omega plus an I omega. So this is going to be 2 I omegas. Oh, interesting. Huh. Oh, I think I see what's going to happen. Do you see what's going to happen? No. Oh, good. Well, I'll show you. Check this out. What is this? E I omega t. Well, that's where we use Euler's identity. Now, so we can write this as e raised to the a, and I'm going to do a big set of parentheses, and then we're going to collect terms. This is cosine omega t plus I sine. Question? Am I making a magic step here? Oh, I did. You're right. I did. Thank you. You're right. Thank you, Vincent. Sarah, nice work. Just good. Now you got to keep me honest. Okay, then we have a minus e to the minus I omega. Well, this is going to be, I'll put the minus, put a parenthesis here, minus. This is going to be the cosine of a negative omega. The cosine is an even function, so the cosine of negative omega is the same as cosine of omega. Yeah. Cosine omega t. Plus sine. The sine of negative omega t becomes, right, it's an odd function, so it becomes minus I sine omega t. Parenthesis, all of that is a times 2 times I times omega. Oh gosh, this is my favorite moment. Do you know why? It's because I get to use another color, and I'm going to just do the unusual. I'm going to slash. Look at that. I have a cosine of omega t here, minus a cosine of omega t here. Oh, there's some more slashing coming up. Does anyone see what it is? Look at this. Here's an I. Well, you know what? I won't do it that fast. I know I'll make a mistake. This is e. I'm going to just pull it out in front. E to the a times t. I have an I sine omega t minus a negative I sine omega t